Thank you to Professor Lee for the kind introduction. So I'm very happy to be here to give the last talk of this workshop. So in this talk, I will talk about semantic communication, which has been the research focus of our group over the last 2 to 3 years. So we actually work on semantic communication from different aspects, like both from theory to deep learning implementation and also resource allocation, different aspects. So, but today I will focus on like generative modeling based semantic communication, which I believe it solves the key problem of semantic communication, which is to send as less data as possible. So I first start with the background. So why semantic communication becomes really popular lately? That's because like so over the last few decades, the capacity of wireless communication has increased very fast. Like each 10 years, the capacity will be 100 times of the last generation. So for the next the coming decades, because of this newly emerged application like Internet of Things, VR, MR, autonomous system, and etc., the demands for wireless communication will also grow exponentially, but the capacity of the wireless communication system are like more or less, we believe, are more or less saturated. And to further increase the capacity, we may need to use like a higher frequency band, like a terahertz communication, or more antenna or denser base station. Like all these kind of implementation will be very costly and will have a lot of technical challenges. So we are thinking of like we can solve this problem from the other aspect, like can we send less data but still achieve the desired information, still meet the application requirements. So we can see like a very simple example. For example, if we want to send an image like this, the traditional ways like we do like a JPEG, we first do to encode it into a bit string. This may be like a 1 MB. And then we apply channel coding, some physical layer transmission algorithm, and the receiver we decode it to get the original image. So the other way is like we can extract the highly compact information, semantic information of this image. For example, we can get a textual description of this image. This is like a green lake and surrounded by mountains. We can send this very compact semantic information to the receiver, and the receiver can use some certain kind of generator to generate an image, which may not exactly like the original one, but still for some conserve the purpose of seeing a beautiful scenery picture of green water and the mountains. So that's the basic idea behind of all the research I'm going to talk about today. And of course, we use deep learning technique to achieve this kind of purpose. So there are a lot of work on semantic communication, and most of them are based on deep learning. So the benefits of using deep learning for semantic communication are listed in these slides. So the first one is like, so the whole system is trained in end-to-end manner. So it will optimize specific to task. So for the traditional like source coding, channel coding, they design for general purpose. So for a spatial task, it may not be optimal, but with deep learning, we can train the whole system in an end-to-end manner. So we can use the loss specific to task. So it can be like theoretically, it can like learn optimal encoder and decoder for a certain task. So the second benefit is like so we actually, if we can learn the knowledge, so the parameter of neural network actually contains the knowledge we learned from data during the training process. So a third one is like with Professor Dr. Liu has also mentioned this, like with the increase of with the more data, we can improve the performance of deep learning based system. So if we there's also, I also going to show one of our work which achieve this kind of characteristic, like we can continuously improve the performance of a deep learning based system with the accumulation of data, or we can say experience. So the last is like now like deep learning is like a very hot topic, and they are also like a hardware designed for deep learning models and algorithms. For example, NVIDIA has been developed like AI RAN Alliance, and Qualcomm and other chip developed, they also have products that are specific for AI acceleration. So this make the practical implementation of this kind of deep learning based semantic communication more possible in the future. So this is like the initial work on like joint source channel coding or like a semantic communication. This is actually a work of my PhD supervisor, Dennis Gundus. So we can see compared to like a traditional method, it achieves certain performance gain in the low compression ratio area compared to like a traditional method. But the gain is still very not very significant, and at least not as significant as we want to be. So they actually we want to like achieve like to meet the demands, we want to achieve like highly efficient or extremely efficient communication. So one idea is to use the recently like very popular AIGC technique. So this has also been mentioned by a lot of speakers in this workshop. Like we have ChatGPT, and we have also like other generative models for other model of data, like Clips is for visual and language generative model. So it's for in general, the generative model has the power of generate high quality data from a very low dimensional latent representation. For example, like this image in these slides, it is generated by Midjourney with like a short paragraph of description. So we can see compared to the text description is like a very short, very like a very low dimensional like description, but we can generate it a high dimensional image. So all the work I'm going to introduce in this talk is based on this idea. So we want to like use the generative modeling to achieve highly efficient semantic communication. So this also has been introduced by Professor Lee from the last talk from yesterday. So the generation process can be described simply by this equation. So we can, so for example, to generate an image, we denote it by X. We can apply a generator on like a latent vector or latent variable Z, and we can get the a generative image. So we can use this generator, we can use this generative modeling to do the encoding and the decoding of images. For example, images, it can also apply to other type of content. So for the encoding process, we can use the inversion. We can use the inversion of this generation process. We can apply G, the inverse of G to on an image X and get its latent representation Z star. And for the decoding process, we can again apply the generator on Z star and get and recover the original image G hat, X hat. So that's the generative modeling of this encoding and decoding process. So by applying generative modeling in semantic communication, we have like 4 key challenges to address. So so the first one is, of course, like is solved by generative modeling itself. It's like we reduce the dimension of latent representation. The second one is like how to resist channel noise. Then the third one is like so generative model always generates something that may not exactly resemble the original image. So how can we better preserve the original content? That's also a big challenge with this kind of generative modeling. So the last one is like, as I mentioned before, so deep learning has this advantage of improving performance with more data. So how should we design the CCOM method such that the transmission performance can be continuously improved? That's also another interesting question, interesting problem we can try to solve. So I'm gonna present some of our works, like from on like a speech transmission, image transmission, and last I also gonna talk about the distributed training of large model, which is not exactly semantic communication, but can be applied to semantic communication to solve some of these challenges listed here. So our first work, this is actually we started working on this problem like 2 or 3 years ago when ChatGPT has become like very popular. So on this work, we want to send a speech and we want to do speech to text transmission and speech to speech transmission. So for this problem, we think like we want to send a highly compact semantic information. So what is semantic information in a speech content? So a very straightforward answer is the text description of this speech. So our motivation is that we want to only send the semantic information to the receiver, and then we use generative model to recover or reconstruct the speech from this received semantic information. So we design a semantic communication model like this, which is kind of complicated, but it can be divided to 4 main modules. So the first one is like a soft alignment module. So for this module, the purpose of this module is to extract only text-related semantic features. But here we don't extract semantic features in word level, but in like a sub-word level on the purpose to have a much smaller vocabulary. So the purpose of this module is like to extract only the text-related semantic features. Then it's like we further reduce the redundancy of the extracted semantic features by redundancy removal module, which removes like more semantically irrelevant features from this from the output of this soft alignment module, like everything after end of sentence, or like some space between some extra space between subwords. And the receiver side, we also include semantic correct module. The purpose of it is to correct, to guarantee, to increase the correctness of the recovered transcription with a pre-trained language model. So this pre-trained language model is not like necessarily a very large language model. It's very simple, like a distribution-based language model. So for this week work, we reconstructed the speech by generating the speech from the semantic transcription we recovered. So to make the generative speech more natural or more close to the original one, we also design an additional speech information module which extract the duration, pitch, and the power information of each phenomenon from the speech to help the speech synthesis. So that's the main the main framework of this SECOM model for SECOM algorithm for speech transmission. Okay, the last part module is the reconstruction, which we use a generative model. So this is the whole system of this speech transmission SECOM system. So the training of this, we also divided into like 2 stages. So the first stage is to train the the semantic encoder and the semantic decoder to make the generative, the reconstruct semantic transcription more accurate. So we trained with CTC loss and the cost entropy loss. So the second stage, we also trained the channel encoder, the speech decoder, and also semantic decoder speech reconstruction to make to optimize the speech reconstruction. So we train it with cost entropy loss and MSE loss of the speech signals. So for this work, we actually achieved so next I will show the results of this system. So for the speech to text transmission, we compare to the existing work. We compare to 3 baselines. So we can observe like 10 reduction of word error rate compared with existing work. And we also noticed that with the introduction of semantic character module, we can see the reduction in word error rate is actually very significant. The dark blue line is the one with semantic character, and the light blue one is the baseline without semantic character. So the baseline means like we don't consider the channel. So we can see there is a remarkable improvement in word error rate. This is for the result for speech-to-text transmission. So we also showed the result on speech-to-speech transmission. So compared to existing work, which is deep SCS, so this is the size of their channel symbols. It's like the amount of information, the amount of channel use they are using. And this is like the proposed algorithm, proposed method. So we can see there is a significant reduction of the number of transmitted symbols. And for the quality of speech reconstruction, we can see that in the MOS, which is like objective, subjective metrics that evaluated by 20 native native English speakers, we can see the our reconstruct speech actually is even like better than the existing method, as well as in the AICIT DTW metrics as well. So in terms of transmission efficiency, that's actually very remarkable. For speech-to-text transmission, we only use 15% of the amount of information sent by the existing work. And for the speech transmission, we only use 0.2% of the amount of information, while achieve comparable speech reconstruction quality. So this is our first work with on semantic communication with generative modeling. So from the results, we can see with generate. So this is give an answer of what we should use for semantic communication. With this generative modeling, we can achieve a significantly or extremely high transmission efficiency. So following this work, we actually work on more on this kind of generative modeling for image transmission as well. So in this work, we use Qianqian generative model. We use Qianqian inversion. So under the transmission, we use Qianqian inversion to extract a highly compact semantic information from the input image. And then we use, to train the semantic is very time consuming. So we also to make to answer the second challenge I mentioned earlier, to resist channel noise, we use normalizing flow to change the distribution of the latent output of this Qianqian inversion and make it more robust against channel noise. Also with this kind of generator we are using, they have a very advantage of they will have disentangled semantic information that's a different part of the latent code refers to like a different semantic features, like for facial image, like some part of the latent code refers to your like eye shape, and some part of the latent code refers to like to the mouth. Some part of the latent code refers to hair, like and so on. So for this kind of disentangled semantic representation, we can have some kind of privacy filter. We can say, oh, this part of the code we are private, so we cannot send it. So we also introduce a privacy preserving mechanism that will replace the hidden latent code with some knowledge base, and which will also help the reconstruct the image more naturally while protecting privacy. So the Qianqian inversion process can be like described by this kind of this equation, which we did like an inverse process of the generative of the generator, where we find latent code in the latent space such that the generated image of this latent code is close to the original image. So this can be like this latent code can be derived by gradient descent, like to find best latent code Z to which can generate the original image the best. So we use normalizing flow to also change the distribution of the latent code to Gaussian in order to be more robust to Gaussian channel noise. So this here is the result of like apply normalizing flow compared to we don't use normalizing flow. We can see the improvements in terms of like PSMR is significant in this case. So again, with this like a generative model, we can achieve significant highly transmission efficiency. Like compared to the original work of DeepJSCC, we actually only need to send like 0.3% or like 0.03% of the data to the receiver. So actually, Dennis also have a lot of work on this kind. They also have work on like a generative modeling as well. So this work is like done last year. So by then, like this work still achieved the kind of the state of the art performance, but there are a lot of other works coming out after. So as I mentioned before, so one of the advantage of deep learning method is like the performance can be continuously improved with the accumulation of experience or data. So in this work, we are trying to achieve that. We're trying to continuously, or like we're trying to continuously improving the performance of SECAM method after implementation. So so the contribution of this work like is in two parts. So the first part is like in our last work, we still apply is normalizing flow and the channel model to make the system to be robust against channel noise. But here in this work, we apply a channel-aware gain inversion approach, which we consider both the power normalization and the channel noise in this gain inversion process. Here we use this PN and which is denotes the power normalization operation, and this we also include the channel noise in this gain inversion process, and also we also look we also consider the LPIP's results. LPIP's like the distortion when we are doing the gain inversion process. So with this kind of design, we don't need any more channel encoder and decoder, and will simplify the whole system. And also to achieve this is a very actually originally we want to apply like a continuous training to achieve this kind of involving performance, but then we found like a simpler realization, which is this semantic caching mechanism, where we simply cached the sent semantic code, sent latent code, and for each transmission, for each image, we will look up in the cached content, cached latent code. So if we find a similar code in the cache, we will not send that code. We will not send is like a latent code. Instead, we will send the index in the cache of the corresponding latent code in the cache space. So in this way, we can avoid transmission redundancy. We can avoid the transmission of similar latent code, which has already been cached in the storage and the transmitter and the receiver. So which can be further improve the transmission efficiency. So this is the results. Like we send 100 images, 100 images one by one, and we can see from this figure that the BCR, which is the which is like the bits per pixel, let's say, which is equivalent to bit per pixel. We can see that the amount of information we need to send for each image is has this kind of decreasing trend, although like it's like fluctuates a lot. That's because like each image, they have different kind of semantic characteristics. So one image they may be very similar to previously sent image. So for this image, we can send less data, but one image we can be like very different from the previous sent image. So we may send more. So, but overall, we can see the overall trend of this curve is going down. And when we calculate the average, the running average actually is going down. So this actually so meets our purpose of like this design. So we want to achieve this continuously improving performance. We want to see this kind of decreasing compression ratio. So on the right-hand side is the image reconstruction quality. So as like for other generative model-based semantic communication method, so the PSMR is always worse than DeepGSCC or worse than traditional method. But in terms of perception, image quality, LPIPs, we can see. So with the same PCR, the perception quality of this method is actually, by this method is actually better than other existing approach. We also, here is like a visual comparison of the reconstruct image. We can see even under a very bad channel condition with SMR of 0 dB. So by the proposed method and also inverse JSC, which is also used generative model, we can see the facial image are still very like a clean and can be the perception quality is still good. But for like a deep JCCC with SMR of 0 dB, so the photos are very blurred or like unrecognizable compared to this generative model based method. However, we noticed that so although like the image, the quality of image is okay, but we can observe that this kind of generative model, it shows a different person. So for example, for the first row of this picture, we can see like this, the original picture and the reconstruction image, so they are actually different person. They are like their eyes and for some part of this face. So like the nose and the mouth, they are very similar, but they are actually different. So this actually is the one of the challenge I mentioned earlier. So with generative model, it's very hard to preserve like the original image, to resemble the original image. So we actually have ongoing work which use this concept of inductance. We apply this kind of inductance term into the diffusion process, into the generative process, which will guarantee, which will make sure the semantic information extracted from the original image and the transmitter and the received image are as close to each other as possible. So I don't like I will not introduce like in details of how this works, because this work is still in preparation. We are still writing up the papers. So I just show some of our results we obtained here. So from this visual comparison, we can see that with this like inductance guaranteed image transmission, so from this result, we can observe that compared to other methods, the facial image we generated actually are the same person as the original one. So we preserve more kind of semantic similarity, more like we have better construction of the original image with this technique. We will put this paper soon in archive. So if you are interested, you can also go check this paper. I have mentioned like like our work on speech transmission and image transmission with generative modeling, which has showed the power of generative modeling in semantic communication. So, and the last part of this talk, I would talk about our work on distributed fine-tuning of large models, this is actually not directly related to semantic communication, but we are also working on to apply this method on like semantic communication. So the first work is like we actually do like a very system work. So this is very like there are a lot of engineer work in this in this problem. So in this work we trying to fine tuning large language model on personal owned devices. This is motivated by the application of kind of personal assistant. We want to fine-tune a large language model, particularly like for personal use. We want to customize a large language model for each person. Use only the personal owned mobile devices. So the benefits of it is like we can use user-specific data. So we can use the data on your personal mobile phone that you don't want to share it with any company or with any like or you don't want to send it to like some cloud servers. So we will keep the data in your local devices, but we will still be able to use it to train your personal large language model. And also it's now like a training large language model is super expensive. Like the GPU is like a not only very expensive, but also very difficult to buy. So we want to exploit local, any kind of computing resource as much as possible. So we designed a system like which can fine tuning large language model on mobile devices. So the challenge here is like so the mobile devices actually cannot like the memory and the computation power of mobile devices are very limited. So in this table, we actually show the memory usage of like 4 LLM models and the memory of like most common mobile phones. We can see there is like a big difference. So it's not possible to run like an entire large language model on mobile devices. So we need some kind of collaborative training or some kind of collaboration among different mobile devices. And also, for like mobile devices, they have this kind of feature of highly dynamics. So each person will take is like your phone always go with you. So you are moved around a lot. So your phone is moved around a lot. And also you will use your phone for other applications as well. So the computing power and the available memory is also highly dynamic. So this is another challenge of this problem. And so the last one is like challenge is like so actually each mobile device they have multiple processors. This is not like a challenge. It's more like the thing we can utilize. So usually have multiple processors. However, so for the server, for the GPU, for the desktop GPU, we train it with GPU, not the CPU, because the computer is like the training speed of GPU is significantly higher than CPU. But this is not the case for mobile device. So here in this figure, we show that the computation latency of CPU and the GPU of the same batch is actually not as different as for a server or for a desktop. So we design like a distributed training system, distributed fine-tuning system for LM across different mobile devices based on model partitioning. So we have these 3 key designs. So the first one is like the memory-aware dynamic model partitioning. It will estimate the computation, the real-time computation of each mobile device. It will estimate the computation time of each part of the model, and it will like solve optimization problem to derive the optimal model partitioning points, and then allocated the different submodel to different mobile devices. So also there is also a design, like a small design here is, so usually mobile device, they were all like different device, they will use different frameworks. So for example, one can use PyTorch, one can use like MAN framework. So they will have different formats of intermediate results. So we also write a cross-platform adapter that can enable the collaborative training across different DNA frameworks. So the second key design here is we also introduce an intro device multi-processor scheduler, which is motivated by the fact that so for transformer-based model, they usually have like multiple attention heads. So we can allocate a different number of attention head to different processors in one device, and we can compute them in parallel in order to further reduce for the accelerate the training. So the last key design here is the fault tolerance mechanism, as I mentioned before. So mobile device is, so in this case, the device participating in the training is highly dynamic and may have like a lot of different kind of failures. So we design both like a passive fault tolerant and a proactive fault tolerant mechanism to recover the training to in case any of the failure happens. So this is actually a very kind of engineer work. So you can see from this the author list of this paper. Actually, we actually have like one PhD, one master, and 3 undergraduate students work on this project. So we write like more than 10,000 lines of code. We like evaluate in different situation and different and evaluate with different models, different tasks. So it takes a lot of work. So we were able to successfully fine-tuning like a billion size LLM using only 3 mobile devices. And here we show the memory usage on each device with the proposed method, which is called confident here. we can see that the memory usage by the proposed method is significantly lower than just use one device to fine tuning. Actually, here, so here actually here is written like 10/24 means like we only train 10 encoder of these 24 encoders of this GPT-2 model. So in most of case, like a single device cannot train like a fine tuning a model alone. So we here compare actually just like train part of the model by in this one device case. But we can still see the significant reduction in memory usage by using the proposed framework, proposed method. So the work I mentioned is using model partitioning. We also so another like a popular research direction on distributed training is federated learning. We also have a work on like federated learning. Here we consider like a non-ID data here. We use LoRa. We combine LoRa, which is low rank adaptation method of fine tuning retrained transformer models. So we work on this problem. The reason we work on this problem is we observe that if the data is non-ID, so we use the LoRa model in a federative learning. It will make so the model wouldn't converge, or there is like a significant performance degradation. So here we use a very simple method to solve this problem. We simply use SVD-based LoRa with initialization to initialize the low-rank matrix A and B, and with this SVD method, and this. So I will not go detail of this work, but the main idea is like we use a particular designed initialization approach such that so the federated learning of LLM with LoRa will not result in performance degradation. So here is the results of the so we like this shows like the during the training the change of these two metrics A and B. So we can see like federal is the proposed approach with our particularly designed initialization way method, and the FedLR is like the is directly applying LoRa to federated learning. We can see by our approach, so the direction of the variation of matrix A and B is kind of very stable, but for the FedLR, so the direction of the matrix A and B, and also the magnitude of A and B is fluctuate a lot. So that's the reason why by the so this can explain why the proposed method can accelerate the training, because it's going the right direction on instead of fluctuate such this fluctuate, so it will like delay the convergence of the model. So this is the results of the trained model. So on these two data set, we can see that so the proposed method federal actually have better, so the underlying, so the boards means the best, and the underlying indicates the second best results. So in most of case, federal can achieve a comparable result to Fed FT is like a 4-parameter training, so it can achieve like a comparable or compared to other fine tuning, low rank fine tuning method, it can achieve better model accuracy. And also can, so here is also show the training efficiency is like measured by the time required to achieve different of accuracy, like 90%, 95, 99% of the target metrics. So we can see that so the proposed approach federal is the fastest compared to other fine tuning methods in federated learning. So this toolwork is actually not like a very quite related to semantic communication, but we are working on applying it for CCOM system to make a like a more to like achieve like a CCOM system that can be adaptive to different various like environment and the various tasks. So to summarize, so the benefit of using generative modeling for CCOM is like we can see it can achieve achieve significant transmission efficiency by leveraging the generation capability. So this is like the main problem of CCOM. So that's why we are continuously working on this kind of generative model-based semantic communication approach. And also with like this semantic information, it's also with some particular designed technique, it also can have better semantic and privacy preserving property. However, so there are also some underexplored potentials of generative model. So first is like more general semantic communication for different tasks and environments. So for the two problems I showed in this talk, is still like we design a particular model for a specific task. So for like a more general semantic CCOM model, I think what we can one potential way to do that is to exploit the large language model to like kind of understand the task requirements and kind of to select the best model and the best parameter for different tasks. So this can be further explored. And also we did a work on this kind of evolving communication performance, like for CCOM model. It's the work I mentioned before. So the involving communication performance, like for CCOM system, is still like not very well researched. So I think for this, we can use the work I mentioned for the fine tuning of LLM or fine tuning of generative model. Like we can use this continuous learning for like to achieve this involving communication performance. This will be one like a remarkable or very attractive advantage of learning-based communication method compared to traditional method, which the performance is sometimes fixed after deployment. But with learning, we can continuously improve. We deploy the communication method in a specific scenario for a specific task, but with the accumulation of communication transmission experience, we can improve the communication performance to reduce the bandwidth requirement. All right, that's all for today's talk. And at the end of the talk, I also want to do a lot advertisement of position available in the Zhejiang University. So we actually are hiring a postdoc, which is a joint position between Zhejiang University and Imperial College. So the salary is, it says like 400K here, but it's still negotiable. And so for this position, you can stay at least 1 year in the Imperial College. It can be up to 2 years. So the research direction is not necessarily on semantic communication. It's can be in the field of broad field of wireless communication, information theory, and AI. And it will be under the supervision of Dennis and myself. So if you're interested, you can like email me and talk to me. All right. So that's all for today's talk. Thank you.